And we talked about this process once before. The way that we do this is we set up these arrays that have a lower limit, an upper limit, and then a guess, which can just be the middle between the lower limit and the upper limit. And then we set up an array that has all of our eigenvalues stored in it, right? So this is finding the root. And then the last thing we have to do is make sure that these arrays here are used when we search for these eigenvalues, right? We can't just find the same eigenvalue over and over again. We have to put these arrays into the variable information window. So you go to the variable information window, you deselect show array variables, and then you come down here and somewhere, here you put in guess, lower limit, and upper limit, right? So I type these in, and that means that, you know, if I'm doing the fifth element, the fifth variable in this array, I'm going to use the fifth variable in this array, and this array. And you hit apply. And what you should find now is that if you go to the, these are the first 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 eigenvalues right here, right? So anyway, however you want to do that is fine, but you have to be able to find these repeated roots. Okay, so we have our eigen functions, and we figured out all of our eigenvalues, so that's good. We solved the eigen problem. Now we got to go back and solve the problem in the non-homogeneous direction. So if you remember, the ODE that we got in the non-homogeneous direction was this one. It's different than the one we had before, right? Before, when we were doing steady state problems, this was an ODE that was solved by Koch and Cinch. This is a first order ODE, right? So this one is actually just going to be solved by exponentials. But we have to remember that we have one of these ODEs for every one of these eigenvalues, right? So for every solution to this ODE, we get a related solution to this ODE. So that's the non-homogeneous problem. It's this guy right here. This is solved by exponentials. If you don't remember that, you can separate this and integrate it, and you'd find that out. You can just type it into Maple. Maple will be happy to tell you. This is one I think that you might want to commit to memory, since you're going to see it a lot. But this is the solution in the non-hom. So this is the non-homogeneous solution for every eigenvalue. So now I have my theta x sub I, my theta t sub I. I multiply them together to get theta sub I, right? So this is my temperature solution for every eigenvalue, right? If I take this function and my eigenfunctions and I multiply them together, this is what I get. You could leave it like this, but it's a little bit silly to multiply the second undetermined constant by the third undetermined constant, given that that product is just itself an undetermined constant. So let's just call that C sub I. All right. So here's my solution for every single eigenvalue. If I stop and think for a second what this does, it should solve that ODE, or PDE, sorry. It should obey this boundary condition, and it should obey that boundary condition. But what it won't do is satisfy this initial condition, right? We haven't enforced that initial condition yet. So that's the last thing we do, and we do that the same way we did it before. We assemble all of these guys together so we can add them all up, because it solves so far a linear homogeneous problem. So here's my sum of all the solutions, right? And then I just make this solution satisfy this initial condition, right? So this sum, if I plug in time equals 0, gives me this equation right here. And this is the last step, and it's the same as the last step before, in that I have a sum that involves an infinite number of constants over here, right? I need to take advantage of the orthogonality of the eigenfunctions to reduce this sum to a single term, right? I want an equation that I can use to get every single constant, right? So I do that in the same way I did before, which is by recognizing that my eigenfunctions have the special characteristic property called orthogonality, right? So if I take any two of them and I multiply them together and then I integrate from 0 to L, I'm going to get 0 for every single case except for the case where the two are the same, right? So I take this entire function and I multiply it by an eigenfunction, and then I integrate from 0 to L. And what that should do is get rid of every term in this equation except for the one where I is equal to j, except for the term related to the specific eigenfunction that I multiplied by. So that gives me this equation here, right? If you look at this, what did I do? I multiplied the left side by an eigenfunction and integrated from 0 to L, so that gives me this equation here. Sorry. And then I took every term on the right side and I multiplied it by an eigenfunction and integrated from 0 to L. So that gives me this equation here. So I can get an equation now for every one of my constants. It involves doing 1, 2, 3 integrals. These are not difficult integrals. They're really easy if you know how to use Maple. So somewhere here I have Maple. This is integral 1, right? I get this equation here. This is integral 2, I get this equation here, and this is integral 3, I get this equation here. And I can literally, I can literally just copy this whole thing and paste it into ease if I want to implement it. And that's what I did here, right? I copied the whole thing. This is integral 1, integral 2, and integral 3. And then this is that equation that gives me c sub I. So now I've got all of my eigenfunctions, all of my eigenvalues, and all of my constants. I've got my solution, right? Here's my solution for theta, right? I just add up all of these terms, however many I want. I'm doing 10, but you could do as many as you want. Don't forget to add t infinity at the end, right? Because theta is t minus t infinity, and you have your solution, right? And that's separation of variables. Again, hopefully by this point the steps are starting to make sense to you because you've done them or seen them a couple times, right? The tricky part a lot of times, as I said before, is actually the first step, which is taking a problem that by itself can't be solved using separation of variables and figuring out how to turn it into problems that can be solved using separation of variables. So in your homework, I'll try to walk you through that process for a problem that's a little bit more tricky than the one that we did here. One thing we can do before we stop today is we can plot temperature as a function of position or temperature as a function of time, and we can see how well our intuition worked, right? We anticipated for this problem what the solution would look like. We said there was a very short internal time constant and a very long external time constant, and therefore we expect that relatively quickly we would get an internal equilibration happening, but it would take kind of a lot longer for the whole block, the whole material to come to equilibrium with its surroundings. And so that's all I did here. Now here's my initial condition, and then you can see that after we said 700 seconds, this is 500, 1,000, right? We're getting pretty flat. And then after we said 5,600 seconds, we should be sort of well down that exponential curve towards being at 20 degrees Celsius, right? So, not exactly the way we sketched it, but qualitatively very much exactly the way we sketched it, right? We got most of the qualitative features right without doing separation of variables or anything else. Okay, so that's one of the two analytical techniques I want to talk about for transient conduction problems. I think in something like this, you get a lot more out of doing the problem yourself versus listening to me and watching me do it. So your homework will make you go through this process. The other analytical technique that you ought to at least be exposed to is Laplace transforms, right? So that's what we'll do next, is talk about how you can use Laplace transforms to solve transient conduction problems as well. And we're just kind of scratching the surface on this stuff. If you really want to get into conduction problems and analytical and numerical solutions to conduction problems, there is a class after this one called 764, where we basically go kind of a lot deeper into this kind of material.